Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon, everybody. My name is Matt Richardson, and I'm a researcher here at MSR in the Machine Learning Group. I have the distinct honor of introducing Pedro Domingos to you all as part of the Microsoft Research Visiting Speaker Series. Pedro is here today to discuss his book, The Master Algorithm. But before he starts, I wanted to say a few words about Pedro. Pedro was my PhD advisor at the University of Washington, and he has a very impressive biography, which you can all read about in the talk announcement. He's won numerous awards, including the KDD Innovation Award, which is considered the highest honor in the data mining field. And he has an amazing breadth of knowledge and always brings a valuable, fresh perspective to any problem that he wants to tackle. I haven't read the book yet, but I'm really looking forward to it. I've always admired Pedro's writing skills. I remember in grad school, my office mate and I, who were both his students, were impressed that no matter how carefully we would write something, Pedro could always edit it to be more concise, clear, and illuminating. I expect Pedro will have brought the same writing style to his book. So without further ado, please help me in welcoming Pedro Domingos.
All right, thanks everyone, and thanks Matt for the introduction. As you can see, some of my grad students even survived the ordeal and went on to do great things. So I'm here today to talk about the master algorithm and how the quest for the ultimate learning machine will remake our world. So what is this all about? It's about a change that is happening in the world today that is as big as the internet or the personal computer or electricity were in their time. And in fact, it builds on all of them. It affects every part of society. It touches everybody's lives. It touches your life right now in ways that you're probably not aware of. Huge fortunes are being made because of it. And also, unfortunately, and sometimes unnecessarily, many jobs are being lost because of it. Children have been born that wouldn't be alive if not for it. And it may save your life one day. This change is the rise of machine learning. And that's what the book is about. So what is machine learning? If you're already familiar with if you're not familiar with machine learning, this talk should be quite valuable. If you are familiar with machine learning, you'll hopefully get maybe a new view of it than what you had before. In one expression, machine learning is the automation of discovery. It's computers getting better with experience, like we do, learning by themselves. It's a little bit like the scientific method, except it's being done by computers instead of scientists, and as a result, it's on steroids. The algorithms, the learning algorithms, they formulate hypotheses, they test them against data, they refine the hypothesis, they repeat this cycle, again, a lot like scientists do, except it's millions of times faster. And as a result, we accumulate knowledge. In any given period of time, machine learning can accumulate millions of times more knowledge than human scientists ever could. Now, most of this knowledge so far is not very deep. It's not, like Newton's laws or the theory of relativity. It tends to be more mundane knowledge. But, mundane knowledge is what life is made of. What do you search for on the web? What do you buy when you go on Amazon? What are your tastes? If you're a company, machine learning helps you understand your customers better. If you're an individual, machine learning helps you find books to read, movies to see, jobs, even dates. A third of all relationships that lead to marriage these days start on the internet. And it's machine learning algorithms that propose potential dates for you. So there are children alive today who wouldn't have been born if not for machine learning. Let me give you another example. The smartphone in your pocket right now is chock full of learning algorithms. The learning algorithms, let it understand what you say, let it correct your typing errors. They predict what you're going to do, and then they help you, either in response to your commands or even on their own initiative. And they use both their panoply of sensors and all the data going through them in order to do this. And they use GPS to figure out what your daily habits are. They can even compare that with your calendar to figure out if you're the kind of person who tends to be tardy for meetings. They can even use the accelerometers that they have to figure out what your characteristic walk is. And something that I think is going to happen in the fairly near future is that if your smartphone figures out that you're about to have a heart attack, it will call 911 on its own, and it will warn you. So machine learning may well save your life one of these days. Now, with machine learning being so valuable, it's not a surprise that tech companies are all over it. So, for example, you may know that Google, not long ago bought this company called DeepMind for over $500 million. It had no customers and no products just because it had better learning algorithms. But if you're Google and you have a learning algorithm that lets you, predict, whether someone will click on an ad 1% better, that alone is worth, $50 billion or so every year. Okay. Another example is IBM just a month ago bought this medical imaging company for $1 billion, not so much because of what they do, but because they want access to their library of images in order to train their learning algorithms to do things like diagnose breast cancer from x-rays and diabetes and whatnot. The kinds of things that today takes very highly paid people to do. And as a result, people with expertise in machine learning are very highly sought after, right? Peter Lee, right, the director of Microsoft Research, actually said that the cost of acquiring a top deep learning expert, deep learning being, of course, a very hot area in machine learning, is comparable to the cost of acquiring a top NFL quarterback prospect. So the geeks have finally won. Yay. On the other hand, machine learning also has a dark side. It is what's behind the increasing automation of white-collar jobs. Some people say that the NSA uses it to spy on us. I don't know because it's secret. But yes, it's probably true, at least to some degree. And there's even a lot of speculation these days in the media, as you've probably seen, that machine learning is going to lead to Terminator, right? Big bad AIs and robots taking over and whatnot. So I think the take-home message from all of this is that machine learning could be your best friend, but it could also be your worst enemy, depending on what you do with it. Which is why I think we're now at the point where everybody needs to have a basic understanding of machine learning, not just computer scientists or machine learning researchers anymore. And that doesn't mean that you need to understand the gory details of how machine learning works. It's a little bit like driving a car, right? You don't need to understand how the engine runs, but you need to understand, what to do with the steering wheel and the pedals. And I think that most people right now don't even know that machine learning algorithms have a steering wheel and pedals that they can control. Okay. So, all right. So how does this happen? So how do computers learn things by themselves? And this, to a lot of people, I think, comes as a surprise, because they think of computers as just these fairly dumb things that just do exactly what we tell them again and again. And learning requires a lot of intelligence, a lot of creativity, and computers aren't supposed to have that, right? Picasso said that computers are useless because they can only give us answers. Okay? Well, machine learning is what happens when computers start asking questions. In particular, the question that a computer asks, or a learning algorithm asks, is the following: here's an input and here's an output. How do I turn that input into that output? Here's an X-ray of a breast, and the output is there's a tumor here, or no, there's no tumor. And this is the question that the learning algorithm is asking: is like, how do I go from one to the other? And if you give enough examples, it often figures out how to do that better than highly paid, experts can do, like people like doctors and so on. Okay. Now here's maybe one way to look at this, which is traditionally, right, computers had to be programmed by us, right? The algorithms, right? We were the ones that defined the algorithms, right? And then we input the algorithm into the computer, and then there was the data that went in the input, and the algorithm, did something to the data, and out comes the output, right? This is how, most, computers in the world work, today. But machine learning turns this around. In machine learning, actually, the output has become an input. So what goes into the computer now is the data and the output. And what the machine learning algorithm is doing is saying like, if this is what goes in and this is what comes out, then what is the algorithm that turns one into the other? And clearly, if you can answer this question, it's very, very powerful. Okay? And now, the amazing thing is that this one algorithm, right, what's in the computer can produce very, very different algorithms depending on the data that goes in. The same algorithm can learn to play chess, or to do, breast cancer diagnosis, or to do credit scoring, or to do, product recommendations, or whatever. And really, the holy grail of machine learning, and some even say the holy grail of computer science, is to figure out what is the most general algorithm that you can have that does this. In some sense, every machine learning algorithm aspires to be, such a master algorithm, which is one algorithm that is independent of the particular application. But just by giving it data, that one master algorithm, right, it's a master algorithm because it makes other algorithms, can turn into something that is good for a huge variety of different things. Okay? And so what I would like to do is just give you a flavor of how that happens. And it's quite fascinating, right? I think one reason to learn about machine learning is that it's very important in your life. But another one is that it's fascinating because learning algorithms come from all sorts of different areas, including neuroscience and evolution and so forth. And to simplify things a bit, there are 5 main schools of thought in machine learning. Each of these schools of thought has its origins in a different field of science. And each of these schools has its own master algorithm, a general purpose algorithm that in principle can be used to solve any problem. Okay? And to fast forward a little bit, what I'm going to argue is that at the end of the day, none of these people really have the master algorithm. They do have one part of it, and the real master algorithm will come when we're able to combine them all into one algorithm. Okay? So what are those 5 schools? They're the symbolists who have their origins in logic and philosophy, and their master algorithm is inverse deduction. It's viewing induction as being the inverse operation of deduction. There are the connectionists, these days the ones that are most famous. Their idea is to reverse engineer the brain, so they're inspired by neuroscience. Their master algorithm is backpropagation. The evolutionaries, what they do is instead of being based on the brain, they're based on evolution. They say, let's simulate evolution on the computer. So they're inspired by evolutionary biology. Their master algorithm, or the most powerful algorithm that they have, is something called genetic programming. Bayesians, another very famous school of thought in machine learning, their origins are in statistics. And in essence, their master algorithm is probabilistic inference, which is really how you apply Bayes' theorem, which is what what Bayesians take their name from. And finally, the analogizers. This is learning and reasoning by analogy. They actually have origins in many different fields, but perhaps the most important one is psychology, because there's an enormous amount of evidence that we human beings do a lot of reasoning by analogy. And again, they have several algorithms, but their most powerful one, or powerful and widely used, is Kernel Machines, also known as support vector machines, which until like the recent upsurge in connectionism was actually the dominant approach in machine learning. Okay, so let's see a little bit more what the basic idea of each of these schools is and what goes on there. So let's start with the symbolists. So here are some of the most famous symbolists in the world: Tom Mitchell at Carnegie Mellon, Steve Muggleton in the UK, Ross Quinlan in Australia. He was actually the first ever PhD in computer science from UW. So in some ways, he's actually local. And he was actually on my PhD committee as well. So here's the basic idea in inverse deduction. This is the idea that we're going to solve learning in the same way that mathematicians solve things by defining inverse operations. So for example, addition, right, gives us the answer to the question, if I add 2 and 2, what do I get as a result? Subtraction, the inverse of that, is the answer to the question, what do I need to add to 2 in order to get 4? Okay? And the answer, of course, is 2. And the basic idea in inverse deduction is essentially the same, right? You say, well, deduction, right, is going from the general to the specific. Induction is going from the specific to the general, so it's the opposite. And so similar to addition and subtraction, right, deduction gives you an answer to the question, if I know that Socrates is human and that humans are mortal, what follows? Well, it follows that Socrates is mortal, of course. Okay? And now what is induction? Induction is asking the question, what knowledge am I missing such that if I know that Socrates is human, I can infer that he's mortal. Okay? And of course, the answer is that, what's missing is the rule that humans are mortal. And now once I've acquired this general rule, I can use it, I can apply it to other people. I can combine it in arbitrary ways with other rules to potentially form very complicated chains of reasoning. Now, of course, I wrote this in English, and computers don't understand natural language yet. So in reality, on the computer, this is represented in something like first-order logic. But the idea is the same. Okay? And here's an example of the power of inverse deduction. You see this picture here? There's a biologist here, but it's not this guy. It's not the guy in the lab coat. This is actually Ross King, a computer scientist and machine learning researcher. The robot is this machine. The biologist is this machine here. That machine is actually a complete robot scientist in a box. It uses inverse deduction to come up with new knowledge of molecular biology, starting from knowing the basics, the central dogma, DNA, proteins, and so on and so forth. And then it formulates hypotheses. It actually carries them out physically on its own, right, using microarrays and sequences and stuff like that. And then it refines the hypotheses or rejects them and keeps going. And this robot is called Eve. It's at the University of Manchester, and last year it discovered a new malaria drug. Now, the interesting thing about this is that once you have one robot like that, you can make 1 million. And now you've just doubled the number of biologists in the world. And then you can make 10 million, and then, and then maybe you will cure cancer one of these days, much sooner than we would otherwise. Okay? Now, the connection is they think symbolists are mistaken. Right? The idea in symbolic learning is that you can do it all at a certain level of abstraction without worrying about the substrate. In essence, the way mathematicians and logicians prove things. But the connection is to well, no, you're not going to get there that way. The best learning algorithm in the universe is the one inside your skull. It's your brain. So let's reverse engineer the brain and come up with a general purpose learning algorithm that way. And the most famous of all connectionists is Jeff Hinton. He started out as a psychologist. These days, he's mainly a computer scientist. But his goal in life for 40 years has been to figure out what is the algorithm by which the brain learns. And he's pretty sure that it can be encapsulated in one algorithm. And he's been doing this since the 70s. In fact, he says that at one point, he came home from work very excited, saying, yay, I've did it. I figured out how the brain works. And his daughter said, oh, Dad, not again. But, these days, his ideas are really starting to pay off. In particular, he was one of the co-inventors of backpropagation. And backpropagation these days, is everywhere. Two other famous connectionists are Yann LeCun and Yoshua Bengio. Yann is now the director of AI research at Facebook. So how do we do this? Well, the way we're going to reverse engineer the brain is as follows, right? The brain is made of neurons. So what we're going to do is we're going to build a mathematical model of a neuron. We're going to build the simplest model we can that works essentially the same way a neuron does. And then we're going to connect those neurons into a big network. And then, of course, the problem is how do you train that network? And that's where backprop comes in. So neurons have dendrites. Impulses come in the dendrites. If the sum of those impulses multiplied by the strength of the dendrites exceeds a threshold, then the neuron fires what's called an axon potential. Right? You can think of a neuron as being, a cell in the shape of a tree. These are the roots. The axon, is the trunk, and the discharge goes down the trunk to the leaves, to the branches and the leaves, and then it connects with other neurons at what are called synapses. And the basic idea behind connectionism, and a hypothesis that we believe is true about the human brain, is that everything you know, everything you've learned in your life, is encoded in the strengths of those connections. So the whole question is, well, how do you learn those connections? Well, first of all, here's a neuron, but in math instead of in biology, right? And what I have is a bunch of inputs. I multiply each input by a weight. I sum them all. So I'm really just doing a weighted average of my inputs, nothing very complicated. And if the result is above a certain threshold, then the output is 1, meaning, I've detected something, let's say, and otherwise it's 0. Now connect this into a big network with lots of layers, and in fact, the term deep learning comes from the fact that it's neural networks with many layers. But now we have this very difficult question, which is, Okay, let's say I'm trying to learn, I don't know, to recognize cats, right? In comes a picture of a cat. I compute the values of the neurons, and then the output should be 1. But the output is actually 0.2. So now how do I fix the problem? Right? This is what's known as the credit assignment problem in machine learning, is like, or maybe more precisely, the blame assignment. Because when this is computing the right thing, nothing needs to happen. When it's making an error, some connections somewhere have to change. And for a long time, people didn't know how to do that. That's the problem that backpropagation solves. And in essence, the backpropagation solves the problem by saying, well, I know there's an error of 0.8 here, and you have a small weight, you have a large weight, so maybe you need to change more because you're more responsible for the error. And so now there's the corresponding error here and here. If I change you, how much will we improve things? Well, how much is each of the weights responsible for that? Maybe something needs to go up to make the neuron more likely to fire. Maybe something that is making a negative contribution needs to go down so that it's not preventing the neuron from firing. Okay? And in essence, this is what backprop is doing. And as I mentioned, backprop these days under the name of deep learning is used for all sorts of things. Particularly things to do with images, retrieving images, understanding videos, and also for speech. Right? Like the Skype, as you may know, like the Skype simultaneous translation system at heart is using deep learning for this. But one very famous example of this that was actually on page 1 of the New York Times is the Google Cat Network. Okay? This is a network that folks from Stanford and Google built. At the time, it was the biggest neural network ever. It has on the order of 1 billion parameters, I think. And they basically trained it by having it look at YouTube videos. Okay? And since on YouTube videos, the single most frequent thing that they found was cats, right? Because people love to post videos of their cats, right? So, so the network, can actually, learns a lot of things besides cats, but cats having the most data was the one that they learned best, and so it's become known as the Google Cat Network. Okay, now, the evolutionaries say, well, sure, the brain, that's fine, you can fine-tune the connections between your neurons, but how did the brain appear, right? The real master algorithm is not the brain, it's evolution. Because evolution made not only the brain, but all of life on Earth as well. Now, that's a powerful learning algorithm. And indeed, biologists, many of them do think of evolution as pretty much an algorithm, and we have a rough sense of how it works. Now, the first person to actually, start pursuing this idea was John Holland back in the 60s. He actually died recently. But then a bunch of other people followed, in particular, so John Holland invented what are called genetic algorithms. John Koza, went the next step by inventing genetic programming. And, and Hod Lipson is one of the people today who are doing, many interesting applications of genetic learning. So what's the basic idea in genetic algorithms? It's quite simple, right? It's, in the same way that we had sort of like a computational implementation of the brain, in the connectionist school, here we're going to have a computational implementation of evolution. You want to solve a problem, right? Let's say you want to build a radio. You start out with a random pile of components. Literally, they start out with random piles of components. Or they start out with, 1,000 random piles of components. Those are the individuals in your population. And then they go out into the world, and you see how well they do. Right? In the case of an animal, it might be how well they survive and reproduce and whatnot. But in the case of something like a radio as well, how much do they capture of the signal that you want to capture and so on. And then each organism or program or whatever has a fitness value. And the ones with the highest fitness get to produce the next generation. So they get to, cross over with some of the others. So, in sexual reproduction, you combine, some, genes from one with genes from the other. In the case of computers, right, the genes are usually just bit strings, right? Because, we don't need base pairs. We can just do it with a bit string. There's also random mutation, and then you get a new population. And then you do the same thing again. And if you do this for enough generations, often amazing things start to happen. Like, for example, people like John Koza have been able to, develop, they have a lot of patents where the things were invented by the algorithm. New ways to build radios and amplifiers and, and low-pass filters and things like that that are different from the ones that human designers created, but actually in many cases work a lot better. So the next step in this, and the most powerful version of evolutionary learning, is what is called genetic programming. And John Cose's idea was this: well, why should we be sure? Nature does this with these strings of DNA, but we don't have to do it with strings, right? A string is a very low-level representation, and it's very easy to muck things up by crossing over a string in some. You could have a perfectly good program, and then you ruin it by basically crossing over in a bad place. So his idea was this: as well, let us evolve, and let us directly evolve programs, right? A program is really a tree of operations, subroutines, etc., all the way down to additions and subtractions and ands and ors and whatnot. So the idea in genetic programming is that your individuals are actually program trees, and then what you do when you build the next generation is you pick a crossover point in the two parent trees, right? The mother program and the father program, if you will, and then you switch the subtrees. So for example, if you had these two trees and you did this crossover at this point, one of the resulting trees would be the one with all the white nodes, which is actually one of Kepler's laws. It's the law that gives the length of a year as a function of the average distance of a planet from the sun. Okay? The length is constant times the square root of the distance cubed. Okay? And as I said, this type of approach has led to many interesting things like new electronic circuits. But these days, perhaps the most exciting or perhaps the most scary thing that the evolutionaries are working on is actually evolving, if you will, flesh and blood robots. Right? This is actually, they're not just doing this as a simulation on the computer anymore. They actually have, this is a real robot from Hod Lipson's lab. They start out with these robots, basically trying to crawl around and stand up and then run faster and things like that. And then each generation of robots, the fittest ones, actually get to program a 3D printer to produce the next generation of robots. Okay? So, so if Terminator happens, this might be the route by which we get there. Okay, so watch out for those little spiders. One of them might be a robot. Okay, so now the Bayesians. The Bayesians have a very different view of things, right? They don't believe in being inspired by nature, whether it's evolution or the brain or whatever. They think we should solve learning from first principles. Okay, and Bayesianism has a long history in statistics. Bayesians are known in machine learning as being the most fanatical of all the tribes. And they have to be, because they were persecuted in minority in statistics for a long time. So they had to become, really determined. And it's a good thing they did, because they certainly have a lot to contribute. And these days, on the back of powerful computers and a lot of data, actually Bayesianism is on the rise even within statistics. Within computer science, probably the most famous Bayesian is Huda Perl, who invented something called Bayesian networks and actually won the Turing Award, the Nobel Prize of Computer Science, a few years ago for that. He's a professor at UCLA. Another famous Bayesian is Microsoft's own David Heckerman. In fact, Microsoft research in its early days was a hotbed of Bayesian learning, and it still is. But of course, now it's much more varied. And perhaps the best known Bayesian these days in machine learning is Mike Jordan. So what do the Bayesians do, right? What do they believe in, right? Well, Bayesians believe in Bayes' theorem. If you have a learning algorithm that is incompatible with Bayes' theorem, you're wrong. In fact, Bayesians love Bayes' theorem so much that there was a Bayesian machine learning startup that actually had Bayes' theorem written in neon letters, and they put it outside their office. Right? So that's Bayes' theorem in neon, shining through the night. So what is the big deal, right? Like, this is a very small expression, right? It almost doesn't merit being called a theorem. The proof is extremely simple, but it's extremely important, right? Bayes' theorem is really just a way to say, well, I start out with a hypothesis. I don't know how much I believe in it, right? So the key problem that the Bayesians are dealing with is uncertainty. Any knowledge that you learn is always uncertain. So what I have is, it's really a combination of these things. There's my prior probability of a hypothesis, how much I believe in this hypothesis before I see any evidence. And the hypothesis could be as simple as a binary decision. This person has AIDS versus this person doesn't have AIDS, right? Or it could be a whole Bayesian network or a whole neural network or decision tree or program or what have you. So you start out with your prior belief, which is how much you believe in your hypothesis before you see any evidence. And then there's this other part, which is the likelihood, which is how likely the evidence is if your hypothesis is true. If this hypothesis makes the evidence very likely, then in return, the hypothesis, our learning hypothesis, that hypothesis is also more probable because it made what you're seeing likely. And then when you combine the two by multiplying them, you get what's called the posterior probability, which is how much you believe your hypothesis after you've seen the evidence. And then you also need to normalize using the marginal probability of the hypothesis, but let's not worry about that. It's just to make everything add up to 1. Okay? And so what you do in Bayesian learning is that you start out with a whole bunch of hypotheses, and then the probabilities evolve. Hopefully some hypotheses become a lot more likely, some of them become a lot less likely, but it may never be the case that there is a single hypothesis that you should believe in. Okay? So the Bayesian view in some ways is very deep in terms of what it says about the world. It says, no, there isn't a single true hypothesis. There's just your prior beliefs, and then the evidence transforms them into posterior beliefs. Now, Bayesian learning has been used for all sorts of things, but a very famous one that I think almost everyone has benefited from, it actually started here at Microsoft Research, is spam filters. Right? The first generation of spam filters, and today, many of them still are, based on Bayesian learning. And the hypothesis here is this a spam email or is this a good email? And the evidence is things like, the words in the email, right? If the email contains the word Viagra, that makes it more likely to be spam. If it contains free in all capitals, more likely to be spam. If it contains 4 consecutive exclamation marks, that makes it more likely to be spam. If it contains the word your mom or the word your boss, then it probably isn't spam, or you might want to, file it as not spam just to be safe, right? You don't want your mom to get mad at you. Okay, finally, the analogizers. The analogizers are a looser tribe than the others, right? They're really a bunch of sort of like different sets of people that do have this thing in common, that they learn by analogy. By looking for similar, when you're trying to solve a problem, you find similar problems in your experience, and then you try to, transfer the solutions from one to the other. One of the early pioneers in this was Peter Hart. There's this algorithm called nearest neighbor, which we'll see shortly, which despite its simplicity is surprisingly powerful. Vladimir Vapnik is the father of Kernel Machines, also known as support vector machines. Douglas Hofstadter, right? He's a cognitive scientist, and he's the author of Gödel, Escher, Bach. And he recently wrote a whole 500-page book arguing that analogy is all there is to intelligence. It has 500 pages explaining why everything we do is just analogical reasoning. So he definitely believes that analogy is the master algorithm. So what is the idea here? Well, let me illustrate it, using a very simple puzzle. And the puzzle is this. Let's say I give you 2 countries. I'm calling them Pozistan and Negaland. And I give you the map, and I tell you where the main cities in each one are. So, here's Positiveville, the capital of Pozistan, a bunch more cities, and here are some, cities of Negaland. And then my question to you is like, if I tell you where the cities are, where is the boundary between them? Where's the frontier? Okay? Now, you don't know, right? But a reasonable thing to do is to say, well, I'm going to assume that a point on the map is in Pozistan if it's closer to some city in Pozistan than it is to any city in Negaland. Okay? So for example, this line here is the set of points that are at the same distance from this city and this city, and so it's part of the boundary. Okay? And even though this is very, very simple, right, all you have to do is remember the data. You don't actually have to do anything whatsoever at learning time. Right? Peter Hart actually proved the theorem that says if you give this algorithm enough data, it can learn anything. It can learn any function. Right? So in that basic sense of the term, this is actually, a master algorithm. It's completely general purpose. Of course, the question is how much data do you really need to learn, and how efficient is it? And this algorithm is not ideal for a couple of reasons. One is that notice there's a lot of things that you really don't need to remember. If I threw away these cities, right, the frontier wouldn't change. All I should have to keep are what are called the support vectors. The support vectors are the examples that cause the frontier to be where it is. And in fact, support vector machines take their name from the support vectors because they just figure out what those are. The other thing that they do is they produce a much smoother frontier, right? This one is a little bit jagged, and it's probably not the true frontier. So support vector machines, throw away all the unnecessary examples, and they produce a smaller frontier. The way they do that is by doing what's called maximizing the margin. Imagine that I tasked you with walking, from south to north, while keeping, all the cities in Pozistan on your left and all the cities in Negaland on your right, but with one extra condition, which is you want to stay as far away from those cities as possible. Okay? Imagine that the cities are landmines and you don't want to step anywhere close to them if you can help it. Okay? And this, so you want to maximize your margin of safety, and that's exactly what support vector machines are doing. Okay? And these algorithms have been used for all sorts of things, but one very famous one is recommender systems. Again, these days, all sorts of learning algorithms get used to recommend products to you, but the original one, and still one of the best ones, is in essence a variation of nearest neighbor. If I want to recommend movies to you, what I do is I find people with similar tastes to yours. If you tended to give, high stars when they give high stars and low stars when they give low stars, then if there's another movie that they give 5 stars to and you haven't seen, then I'm going to hypothesize that you would like that movie as well. Okay? And I've seen it in multiple places that, although I don't think anybody knows this officially, that a third of Amazon's business comes from its recommender system. And 3/4 of Netflix's business comes from its recommender system. So, this thing is really at the heart of what these companies do. All right, so let's take stock of what we've seen. We have the 5 tribes. Each of these tribes has a particular problem that it's solving that the others don't solve. And this is an important problem for machine learning. If you want to have a universal learner, you have to solve that problem. So the symbolists learn rules that you can compose in arbitrary ways. The others don't do that. Connectionists know how to, and they do that using, their master algorithm. Their solution to the problem is inverse deduction, right? Inverse deduction is how you learn these rules that you can compose. Connectionists solve the credit assignment problem using backprop. Evolutionaries discover structure, right? Before you can start fine-tuning the connections in your brain, you have to figure out what the structure of the brain is. Well, evolution, is one way to come up with that, and their solution, or most powerful solution, is genetic programming. Bayesians solve the problem of dealing with uncertainty. They use probability, they use Bayes' theorem, and then they do inference to figure out what the probabilities are after the evidence. And the analogizers actually do something that none of the others can, which is to generalize from very few examples to things that are very different. Remember in the Posistan and Negland example, if all I knew was the location of the capitals of both countries, I could already form a reasonable approximation to the frontier. None of the other approaches can do this. And there are, forms of analogy that are much more powerful than the ones that I showed you here. Okay? That even allow you to generalize to completely different domains. Like you can learn, to solve things as a physicist, and then you get employed, to predict the stock market using the same skills that you acquired, right? So humans are able to do this. Analogy is able to do this. The other ones aren't. But here's the thing. As much as each of these tribes really believes in its approach and, and has been very brilliant and very determined in making progress, at the end of the day, if we really want to have a master algorithm, we have to solve all 5 problems at once. We need a single algorithm that actually has all of these properties. And so the question is, well, what would that algorithm look like, right? In some sense, what we're looking for here is a grand unified theory of machine learning. In the same way that the standard model is a grand unified theory of physics, or the central dogma is a grand unified theory of biology. So what might that look like? Right? Well, we don't have that yet, but we're actually making very good progress. In particular, in the last decade, we've made amazing amounts of progress. So here's the first thing to notice, right? These algorithms look completely different, right? But actually, they're not. All these learning algorithms, and many others that I haven't shown, they're really all composed of 3 pieces. The first piece is representation. What is essentially the programming language in which the learning algorithm is going to write the programs that it discovers? Okay? Learning algorithms tend not to program in Java or C++ or anything like that. They program in things like first-order logic, right? Or it could be a neural network. Okay? Now, the first thing that we need to do is to find a unified representation that is powerful enough to do this. And, Matt, in his PhD thesis, found one. It's called Markov logic networks. And what it does is actually it combines logic, which is what the symbolists use, with the graphical models that, that the Bayesians use. In particular, it combines logic with Markov networks, which is a different type of and in some ways a more powerful type of graphical model than Bayesian networks. And really what a Markov logic network is just you have your formulas in first-order logic, in which you can encode basically anything you want to encode, and then you give them weights. If you really believe a formula, you give it a high weight. If you're not very sure, you give it a low weight. And then a state of the world is very probable if a lot of the high-weight formulas are true in it. And it turns out that this representation is a very nice generalization of almost everything that we use in machine learning. So that's the representation part. The second part that all learning algorithms have is evaluation. Evaluation is deciding, if I give you a candidate program, how good is it? Well, usually we decide that it's good because it fits the data well, meaning it makes accurate predictions, and also maybe it's simple, it has other desirable properties. One thing that we can use here is just the Bayesian's posterior probability, right? This is a popular option. But more general, the evaluation, I would argue, should not be a part of the algorithm. It should be something that it takes from the user. You, the user, tell the master algorithm what you want it to do for you. If you're a company, say, maximize my profits, or whatever your goal for that particular problem is. If you're an individual, you say, well, maximize my whatever, my utility, or my, whatever you want. And then the algorithm just goes and optimizes that. Finally, there's optimization, which is really where most of the work goes in machine learning. Optimization is finding the algorithm, the program that maximizes your score out of all the ones that the language allows. So for example, in the case of Markov logic networks, what is the set of formulas and their weights that, for example, most faithfully represents what I see in the world without being overly complex? Okay? And here there's a very natural combination of evolutionary and connectionist ideas, right? We can use genetic programming to discover the formulas, right? We have a population of formulas, we mix and match them, we mutate them, we perturb them, add and remove things, take one part of another, combine it with a part of, part of one combined with part of another, and so forth, right? So we can use genetic programming to discover the formulas, and then to learn their weights, of course, we can use backpropagation, right? In pretty much the same way that it gets used in neural networks. And again, we have many standard neural networks like Boltzmann machines, for example, as direct special cases of this, okay? So, we've made good progress, but of course, we're not there by any means. There's a lot that remains to be done. And my feeling actually is that even if we succeed in completely unifying these 5 paradigms, and I think we're getting pretty close, I don't think at that point we will actually have solved the problem. I think there are some major ideas that we're going to need that haven't been discovered yet. And in some ways, the people who are already working in one of these schools, who are very deep experts in one of them, are not the best positioned for that. You're actually better off, if your thinking is not along those tracks and if you have more of a distance. So we need your ideas. And if you read the book and have a brilliant idea about what the master algorithm should be, please tell me so I can publish it. Okay, let me conclude just by saying a little bit about what I think are the things that the master algorithm will enable that current learning algorithms cannot yet do. And the reason these things need the master algorithm is that, again, all of those 5 problems are present in them. If only one was present, then you could use the appropriate paradigm. But in most of the really important, really hard problems, all the 5 issues are present. One of them is home robots, right? Home robots are coming at some point. We would all love to have a robot that that cooks dinner for us, does the dishes, makes the beds, and so on. But it's a very, very hard problem. Everybody in AI agrees that it can't be solved without machine learning. But also, what kind of machine learning will it take to build such a robot? And I think it is something like the master algorithm that we're looking for. Here's another one. Everybody these days is trying to turn the web into a big knowledge base. There's an effort like that at Microsoft. There's one at Google. There's one at Facebook. There's several in academia. This is the idea that, well, the web is a mass of text and images, which is very hard for computers to deal with. If we can turn that into something like a knowledge base in first-order logic, then instead of issuing keyword queries and getting some pages back, you can actually have a dialogue with the computer, where you ask questions, then it reasons over its knowledge, and it gives you the answers, right? This would clearly be a great thing to have, but again, we can't solve it without machine learning, and we can't solve it without the kind of universal learner that we're talking about here. I think each of the paradigms that we have right now is not enough, and so people try to hack some things on top of the one that they start with, but we need a more fundamental solution. Here's another example, perhaps the most important one of all, which is curing cancer. Why is curing cancer so hard? It's because cancer is not a single disease. Every cancer is different. And the same cancer mutates as it goes along. So somebody's cancer right now is different from the one that it was 6 months ago. So it's very unlikely that there's a single drug that will magically cure all cancers. What you actually need is something like a learning program that takes in the genome of the cancer, its mutations, right, relative to the genome of the patient, which it also knows, and the patient's medical history. And from that, it predicts what is the drug that will be the best for that patient, or a combination of drugs or sequence of drugs. In a way, it's not unlike a recommender system. except that instead of recommending a book or a movie, it's actually recommending a drug to treat your cancer. And this is something that is beyond the ability of any human being to do, biologist or doctor or whatever, because there's just too much information. There's just too much knowledge that goes into understanding how a cell works, right? You don't just need to cure the cancer, you also need to not, destroy the cells in the process or harm them, right? So both the amount of information that you need to bring into this model is too large, and the number of things that you have to attend to at diagnosis time, even just the sheer number of drugs that you might be able to use, are beyond any human being. But I think with something like the master algorithm, we will be able to do it. And, and there are many people working very energetically in that direction. So finally, let me mention this idea of 360-degree recommenders. The kinds of recommendation systems that we have today recommend one type of thing. And they based on the knowledge that one of these companies has of you. Right? Amazon can recommend things based on your clicks on the Amazon site. Netflix can recommend things based on, on what you do on Netflix. Same with Facebook and Twitter and so on and so forth. But what you would really like to have is a model of you that is based on all the data that you've ever generated. In fact, in the limit, that's generated from your stream of consciousness. Imagine what you're doing being recorded, video and audio recorded, continuously. And now what you want to do is learn on that a very, very good model of you that knows you much better than any of these models that are based on a sliver of your data. And then that model helps you, at every step of your life. Recommends things, large and small to you, like from books to read to who to date and, and where to go to college and what house to buy and whatnot. Okay? Again, this involves all of the problems that we talked about. So I think, current machine learning algorithms are certainly not up to that. But I think if we discover the master algorithm, we will be able to do this. And then I think your personal model will become, even more important to you than your smartphone. Like living life without the help of your personal model will come to seem impossible. And with that model, you will live a happier and more productive life than we do today. Thank you. I'll take questions.
So how do these popular algorithms such as decision tree and boosting those assemble algorithms into 5 tribes?
Yes.
6 tribes or no?
No, yes, so good question. So decision trees are very much a symbolist algorithm, right? They come from the symbolist school of machine learning, like Ross Quinlan is a very good example of that, right? Going all the way back to the 60s. Boosting is a simple way of combining algorithms. So you could think of these ensemble methods as a step on the way. They're the simplest way you can combine these algorithms, right? And they're very successful, but they're also somewhat shallow, right? It's not a deep combination. So it works, but we should be able to do better.
Thank you, Pedro, for the talk. Very quickly, I wanted to get your thoughts on, this is more a philosophical issue, behind what's the ethics behind the universal learner. Obviously, when the universal learner will provide suggestions is one thing, but when the universal learner provides actual choices, that's another thing. What are your thoughts on that?
Well, obviously, and I didn't have time to go into that, the implications of this for you and for society are very large, right? Who makes the decisions and why, and who are the algorithms serving, right? The thing to realize is that today already, a lot of the decision is being made for you by an algorithm, right? Is, for example, if you want to, take your pick, right? Buy a book, right? Or even, let's say search results. The learning algorithm already throws out 99.999% of things. Then from the 10 that you look at, you get to pick, right? So you're ultimately in control, but only of what was already pre-selected by the algorithm. And the more the information society grows, the more choices there are, right? This is the great thing. We have amazing choices today, but we don't have the time to make them. Which is why having a model is good, because what that model does, it's going to make most of those choices for you. Finally, it's going to leave the ultimate control to you, and it's going to learn from what you say, right? So I think this will be very useful. At the same time, you want to make sure that that model is owned by you, right? There's a little bit of danger in the model being owned by someone who has a conflict of interest. Like Sergey Brin says that Google wants to be the third half of your brain. Well, great, but you don't want the third half of your brain to always be trying to show you ads, right? That would be a little worrisome, right? So, there are a lot of, issues to consider here. Yeah. Yeah.
So, kind of looking at an early attempt and the current attempt. So look at Sitecorp and also looking at Watson.
Right.
And what did each of those do poorly, and what good things came out of those.
Yeah, so psych was the ultimate attempt by, so like in AI, there's sort of like the knowledge engineering school, right? We're going to build intelligent systems by writing in all the rules manually, right? And then that didn't work because there are just too many rules. In fact, if you don't learn, it doesn't matter whether you put 10,000 or 100,000 or a million rules, your robot or your system will always very soon come up against something that it doesn't know. So that was a failure, but it was an interesting failure because we learned something from it. One thing that we learned from it is that you got to use machine learning. And Watson uses machine learning a lot. But it uses, it uses sort of like this big hodgepodge of hundreds of different learning modules. And this is, I think, Watson, well illustrates the problem with trying to build AI by just treating it as a pure engineering problem. You can engineer a system that will solve Jeopardy, but will that work well on other problems? Well, so far, there's no evidence that it really does. Yeah, so I think we need, it's because intelligence is complex that we need the simplest algorithms that we can get. So I think both of these were useful, but neither of them is really the answer.
Have you seen machine learning being used in the legal field to make decisions? I mean, from recommendations of...
Yeah. No, let me give you, exactly. This is one of those unexpected examples where you take this highly qualified white-collar work, and it's actually more easily automated than construction work, right? So one example of this is, the analogizers, actually one of their favorite applications is law, because of case-based reasoning. Right? People in the law reason by cases, which is they look for a similar case and then they say like, oh, the Supreme Court said this, and this case is analogous, so how do we do that? So this is one successful application, and they've had things like, somebody did a study to see whether you could predict the outcomes of various, decisions, and the winner was an algorithm of this type, much better than the human experts. Another example is e-discovery, right? Two companies have a lawsuit, they're allowed to look through each other's documents. These days, there's like millions of emails, right? And they used to basically employ, junior lawyers to go through those piles of stuff. And it turns out that if you do that using some of these learning algorithms, they actually do better than the human beings, right? I think partly it's because the human beings are very bored and no one's really, paying attention to what they're doing, but still, yeah.
Are you afraid that someone would hijack the system, basically, and learn information about you? For example, in strategic games, if you know how the opponent thinks, you can move him into a trap, or maybe just subvert the system to give you the wrong advice.
Yeah. So yes, let me make sure I understand. So my sense, like, what if I have an enemy and that enemy is in control of the learning algorithm?
Well, either in control or he just knows what goes into the learning algorithm.
No, yeah, very good.
About you.
Yeah, actually, I had a student of mine, Daniel Lau, who in his internship at Microsoft Research worked on this problem. This is a problem of adversarial learning, right? I built a spam filter, right? I mean, I remember when David Hacken was like, oh, we've almost solved the spam problem because their spam classifier was 99% accurate. But of course, the spammers wouldn't stay still. They figured out how to defeat the classifier. And it turns out it's not that hard. So what you have actually to do is that you have to have a machine learning algorithm that is a combination of machine learning and game theory. We say like, if I deploy this classifier, what is the spammer going to do? And now let me do something that defeats what the spammer does. Like, for example, they would put hyphens, via -gra, which actually defeated, the keyword, search that the learning algorithm did. But if you now look for words with a hyphen in the middle, that actually is even a better way to detect spam. So you need these kinds of algorithms, and it is an arms race, but it's certainly, an active area. Yeah.
Do you think the machine learning algorithm should be centralized, like live in a data center somewhere, or it should be distributed, like living on everyone's tablet, phone, or?
Yeah, this is a very good question, right? So are they going to be centralized or distributed?
Yeah.
I don't think there's going to be a unique answer. It's going to depend on things like how efficient various parts of this are, how much you care about your privacy, right? I mean, a lot of these things these days, even your smartphone, like what they do is like you speak into them and they send it to the cloud, and then the cloud is actually where the understanding is going on. You as the user don't necessarily care, right? So partly it's a question of just engineering efficiency, but partly it's a question of, for example, how safe do you want to be, right? Ultimately, if you don't want, for example, the government to subpoena your data from the cloud, then maybe it has to always be with you, in which case, you have the rights to it. So I don't think there's going to be a unique solution. I do think there's going to be a place for a kind of company that is kind of like the repository of all your data and the company that learns the model for all your data. Whether this is one of the current companies or not is an interesting question. But I think, I think we're going to see things like that happening. Yeah. Mm-hmm.
In terms of pairing machines and humans, have any one of the models been better than the others at things like augmented cognition?
Yeah, I mean, the reason these paradigms, continue is that each one of them has successes that it point to, right, in terms of the things that it does better than the others. And often when you compare them with humans, right, there are certain things at which some of these algorithms are better than human beings, right? A famous example of that these days is DeepMind, right? They can play a lot of Atari, games better than any human being. At the same time, you also see the things that they don't do very well. So, DeepMind plays Pong very well, but Pong is basically just making this, racket go up and down. It can't play Pac-Man very well. Pac-Man, I've talked to some people there, and they agree, well, for that you start to need reasoning and planning, the kinds of things that the symbolists are better at. So the amazing thing is that you, the human being, cannot do these things as individual things as well as the algorithms, but overall, we're still the best. It's the master algorithm that I think will be able to do things as well as are better than people by combining these things and maybe some others that we haven't figured out yet.
Is there a master scenario or a master test that will verify the master algorithm?
Yeah. So this is definitely an important question. How will we know when we found the master algorithm, right? And I think the essential answer to this is that it has to be an algorithm that solves not just one problem, but many different problems that it didn't see before. So these days when people do tests in machine learning, it's like, oh, I want to learn to do object recognition, so I will give you, a database of images, train on some of them, and then test on the others, right? But that's just with vision, right? The real test is, I will give you a set of tasks to learn on, like, for example, vision and robotics and whatnot, and I'm going to give you a task where the task itself is different from the ones that you saw before, right? So the traditional kind of learning wouldn't have worked. And you have to be able to do more than one. So it's this idea that one algorithm has to be able to do many things at the same time. And if you think about it, this is implicitly what the community already does with machine learning algorithms. Like they learn on these data sets from medical diagnosis or vision or whatever, and then they go test it on others, and they get excited when it does well on those. And in some sense, I think this is what we're going to have to do. Yeah.
So you cited the schools of thought that have adherence and have successes. Is there a notable example of a school of thought that's failed, and why did it fail?
That's a good question. I think the interesting thing about the history of machine learning is that all of these schools of thought failed at some point and then they came back. So, maybe there's minor ones that are not. I mean, so just to be clear, there's other things that I talk about in the book that I didn't talk about here, things like reinforcement learning, for example, unsupervised learning, right? There are, whole subfields of machine learning that I haven't talked about. But I think what is amazing is that, for example, take connectionism, right? In the 50s, when Frank Rosenblatt, first started doing this was like, oh, we've almost figured out how the brain works. And then it died, right? Basically, the symbolists killed it, right? Minsky and Papert wrote this book saying, look, there's all these things that your neural networks can't do. And so for 20 years, they were dead. And then in the 80s, they came back when backprop was invented. And then they faded away again, and the Bayesians were on the rise. And then the next decade, the analogizer were on the rise. And now, deep learning is on the rise again. And some of the more optimistic of the deep learners are like, yeah, we got it, right? We solved vision, we solved speech. Next, we're going to do language and reasoning, and, any day now. I'm not kidding, right? My view is that, if you look at the history, just extrapolate in a naive machine learning sense, there's going to be another 5 good years of deep learning, and then some other school will have another, right? But I think eventually we have to converge to something that actually is not just one school or the other, but the combination of all of them. Yeah.
Do you think that these can be used to solve moral problems, to tell us what's good and what's bad?
That's a great question, right? And, of making moral decisions. And in fact, it's a very pregnant question these days because of the issue of intelligent robots in warfare, right? More and more we're seeing autonomous drones, and in some countries actually have drones that can, autonomously decide to fire. And now, some people say this is terrible and we should ban them. I think that's actually a very bad idea because, it could save a lot of lives to replace human soldiers by robots, and also robots, they don't get angry, they don't get scared, they don't get vindictive, robots may actually have better judgment. But then there's this basic ethical judgment question. And one thing that people are pursuing, like people like Ron Arkin, is you can maybe program certain rules of morality into the robots, like Asimov's 3 laws, right? But the problem with Asimov's 3 laws is that, every one of his stories is about a failure of one of those laws. Just those laws are not enough to figure out what to do in every circumstance. But now, I think the machine learning answer to this question is, sure, you can program those basic things into the robot, but then the robot can learn to make moral decisions by observing what people do. The problem there is that I think if a robot does that, it will be very confused. because we have these moral principles, but most of the time we don't follow them, right? So I think at the end of the day, in this as in many other things, machine learning and AI are actually going to force us to confront. I think we in some ways are going to learn more and more about morality because we're going to have to teach the robots morality, and in that process, I think we're going to have to figure some things out ourselves. So I think the hard part of programming morality into robots is not the programming part, it's the morality part.
What has led to the insight or expectation that there would be one master algorithm, and why couldn't it be 5 or 10? Or?
No, so to be more precise, right, here's an analogy. Think of Turing machines, right? A universal Turing machine is a universal model of computation, right? And there are dozens of other, or even hundreds of other universal models of computation that are Turing equivalent. So it's not that there's only one model, right? It's that there are many equivalent ones. And likewise, there will be many equivalent versions of the master algorithm, just like there are many equivalent versions of, of the laws of physics, right? There's Newton's version, the Lagrangian version, the Hamiltonian version, right?
There's one standard model.
Well, I mean, we could even debate that, right? The standard model is a bit of a patchwork, right? But the point is, right, we want to find the first one, right? We in induction, right, are at the point where deduction was before Turing came up with the universal Turing machine, right? So in some sense, it doesn't matter exactly what form it takes. And, and then there'll be a lot of engineering of variations and whatnot, right? Because, again, these things are probabilistic, so it's a bit different from deduction. But yes, there could be more than one. But at some level, at the end of the day, they have to be equivalent. All of the schools of machine learning have these theorems that say, my method can learn anything given enough data. A neural network can learn anything if it's large enough and you give it enough data. Same with a set of rules, same with nearest neighbor, et cetera. But the problem is, how well can they learn it, right? So it's not just being able to learn it in principle, it's being able to learn it in practice. And in practice, different things may be better for different problems. But to pick another analogy, think of the microprocessor, right? A microprocessor is not the best solution to any computing problem. There's always an ASIC, right? A circuit specific for the application that does better. And yet it's microprocessors that we use for everything. And so the master algorithm, in a way, is for machine learning what a microprocessor is for computer architecture.
So to clarify, there's a difference between the master algorithm and strong AI, correct?
Yeah, so this is another good question, right? So the idea of strong AI is that we can actually have a computer that is not just as intelligent as humans, but actually is indistinguishable from humans, right? The master algorithm hypothesis actually in some ways doesn't say anything about the strong AI hypothesis, right? The master algorithm is just a learning algorithm, right? It's not conscious, it's not an agent, it doesn't have a will of its own. Now, if you want to create strong AI, I definitely recommend that the shortest path to is to try to invent the master algorithm. Ray Kurzweil wants to invent strong AI by reverse engineering the human brain. I'm willing to bet him that we will figure out the master algorithm long before we figure out how the brain works. And in fact, you can't figure out how the brain works without machine learning. Right? There's this field of connectomics where you take slices of the brain and literally do the circuit diagram, literally reverse engineer the brain. But the amount of information is so large, right, that they are desperate. Like Sebastian Sung is always asking me for machine learning, students who will be postdocs with him to actually use the machine learning to do the reverse engineering. So yeah, I think if you believe in strong AI, this is a good path to it, but you don't have to believe in strong AI to think that the master algorithm is a good, research, direction to work on.
So related to that, humans are very biased. We always think we're right, for example. Do you think the master algorithm will be more towards that way or more statistics-based?
Sorry, humans are very what?
They're very, very biased towards thinking they're always right, so they're overconfident.
Yes, so human beings, exactly. There's this large body of psychology, evidence that human beings tend to be overconfident, right? So we human beings actually tend to overfit in machine learning terms. And I think the beauty of machine learning in some sense is that you have a knob that you can turn, right? Any good algorithm, any good learning algorithm has this knob that allows it to be more, have more bias or more variance, right, as the technical terms go. However, the interesting thing is why do human beings err on the side of overfitting, right? And I think there probably is a reason for that, is that it's not the individual human being that's the unit, it's the group, it's the society, right? If I have 100 people, all of whom overfit, one of them won't be overfitting, and that one will learn something, and as a result, the whole tribe, if you will learn something faster than if all of them were trying to be, as accurate as possible. And maybe there's a similar, again, in model ensembles, we're just talking about boosting, there's a little bit of this. The individual models in the ensemble can be overfit. Right? The decision trees, for example, can be wildly overfit. And then when you combine them, you actually have a much better model. So maybe that's the reason. Yeah. More questions?
Yeah, so in the first couple of slides, you showed that what goes into master algorithm is output and data, assuming, sort of implying that it's supervised learning, but I thought the master algorithm eventually has to be unsupervised learning.
No, yes.
Leave out
No,
that.
no, I agree. So that, this is just a 45-minute talk, right? So that is the supervised version of things. In the supervised version, just data goes in and the algorithm figures things out. Yeah, definitely.
Do you think unsupervised may be the master algorithm?
No, the master algorithm should be able to learn from any amount of supervision. And we already have things like Markov logic networks that can learn from any amount of supervision. Completely supervised, completely unsupervised, or somewhere in between. Okay.
We'll take one more question.
Yeah, one more question.
Do you believe the largest expertise of possible of this hosting can be biology, like come from our own brains, that is so unique that we can simulate it in a computer by 0 and 1?
Yeah, so there are some people who say that, right? Like Roger Penrose says, we will never succeed because the brain is doing this mysterious quantum mechanics. Nobody else believes that. I'm not even sure he believes that. But in general, this is a plausible. So here are two versions of that. One is there is some magic going on in the brain, right? If you're a scientist and you're a reductionist, that can't be the case, right? However, there's a more subtle version of this, which is that the brain is so complex that we will never figure it out. Like, it's like the notion that, like, if we were so simple that we could understand ourselves, we would be so stupid that we couldn't, right? But the thing is that, like, it's not one person trying to understand one brain. It's a whole scientific community of tens of thousands of people over decades trying to understand the brain. So I think we will succeed in the end, and also because the master algorithm can be a lot simpler than the brain, right? The brain does a lot of things besides learning, and it has a lot of evolutionary craft, which we don't need, if what we do want to do is have learning on a computer. And, at the end of the day, we're only going to find out by trying. And even if we don't succeed, I think we will discover much better learning algorithms along the way, so it's definitely something worth doing. Thanks, everybody.